relativistic conformal field theory and nuclear reactions.
Thank you very much. Is it on? So, first, I would like to thank the organizers for giving me the opportunity to give this talk here. I apologize to give a talk for giving a talk at the QCD Meet Gravity meeting. My talk will not have much to do with gravity and only have some tangential connection to QCD through strong interaction. Okay, so this is the plan of my talk. I'm going to first review what is known about non-relativistic conformal symmetry. I will build on this notion of conformal symmetry in non-relativistic setting to talk about non-relativistic conformal field theories that I will define. And then we will zoom in into one example called fermions at unitarity. This is the most important example of non-relativistic conformal field theory since it is realized in experiment and in some approximate sense by neutrons. And we will describe a scaling phenomena in nuclear reaction that I call unnuclear physics. This talk is based on a paper that I wrote with Yusuke Nishida a long time ago, 2007, and also on recent work with Hans Hammer during COVID, and more recent work with my postdocs and student in Chicago, Swam Chaudhuri, who is now at the ICTP, and Mishira Mishra is a student at Chicago. Let's first consider a very simple equation, the Schrödinger equation of a single particle in free space. So these equations, if we have a solution to the equation, we can use several symmetry transformation to generate a new solution. One of such transformation is just multiplication by a phase. That one corresponds to the conservation of particle number. There is spatial translation and temporal translation, and there is also rotation that I will write down on the slide. A slightly more non-trivial transformation is Galilean boost, which we replace x by x minus pt and keep t invariant. Non-relativistic Galilean transformation time remains absolute. If we just replace x by x minus pt, the Schrödinger equation is not going to be satisfied by the new field. But one can correct for the problem by multiplying the solution by a certain phase, which can be, you can check by the trial and error that this is a new solution to the Schrödinger equation. Dilatation is another transformation. We replace x by lambda x and t by lambda square t, and we can generate a new solution. So here I'm being pedantic and multiply the wave function by lambda to the power 3½ so that the new wave function is normalized to 1 as the old wave function. But these are not the only transformation that generate the new solution. There is a quite non-trivial way to generate the new solution by replacing t by t divided by 1 plus alpha t. You can think about that as a combination of inversion, of translation in time, inversion and translation. And if one replace x by x multiplying to the same factor, 1 over 1 plus alpha t, and do some trial and error with the coefficient, the phase and the numerical coefficient in front, we will find that this new solution, this new field, this new function is again the solution to the Schrödinger equation. The real factor in front of this expression can be guessed by the condition of normalization. The normalization of the new wave function has to be 1. But the phase has to be checked by trial and error. But I guarantee that there is such a transformation. So all these transformations form a group of symmetry of the Schrodinger equation called the Schrodinger group. And at the level of the Lie algebra, the infinitesimal transformations form algebra with certain commutation relation, some of which I write in this table. One feature of the transformation of this algebra is that the operator corresponding to the particle number, that is the multiplication by a phase, commuted everything, so it's the center of the algebra. Another interesting feature is that the operator of the Hamiltonian, that is translation in time, the dilatations, and this special conformal transformation C, this complicated one that I wrote down in the previous slide, form a closed subalgebra of the Schrodinger algebra, and that subalgebra is isomorphic to SO2, 1. So this fact actually is known and used in atomic physics. One way to understand how these operators look like in the non-relativistic system is to express them through the density of particle number and the density of current. Suppose we have a theory where psi is the operator at that annihilator particle at point x, and then we can define two operators, the density operator and the current operator. This is the density and this is the momentum density. And then the density of these various operators, not all of them, but various operators of the Schrodinger algebra can be written as an integral of this current density. And another feature that I didn't write down on this slide is that this n of x and j of x actually form a closed algebra. Density operator and the momentum density operator, or when you commute them, you don't go beyond these operators. In particular, the operators j, these operators, form an algebra that is the same, that is exactly the same algebra as the algebra of diffeomorphism space. So by expressing this operator NP, the momentum, the Galilean boost, the special conformal transformation, dilatation, you can actually derive a lot of the commutation relation between these operators. Missing operator here is the Hamiltonian, that in general cannot be expressed in terms of the operator N and J. So the commutator of the Hamiltonian with other operator have to be derived. Okay, so now let's go to non-relativistic conformal field theories. One can roughly define the non-relativistic conformal field theories as field theories where field theories with the non-relativistic Schrodinger symmetry. In this theory, one can follow a lot of things that have been done in the relativistic case to certain extents. For example, one can define the notion of local operators, O of x. These operators can be classified by its dimension and by the particle number n. By commuting this d with O with the operator of dilatation, with the operator of particle numbers. Now here I call it the mass operator. We can find its dimension delta and the particle number n, or its charge. So, for example, for an operator psi, the annihilation operator, the dimension of this operator in 3 plus 1 dimension is 3/2, and its charge is 1, maybe minus 1. This operator, when acting on a state, annihilates a particle, so its charge is minus 1. One can also define the notion of primary operator in the same way as one does in relativistic case. So let me show you on the next slide diagrams that illustrate the notion of primary operators. If we have an operator, by acting on it, that is by commuting it with the translation operator, when one increase the dimension by 1. Translation, acting on commuting with an operator, take a derivative, spatial derivative. We commute the operator with the Hamiltonian, we would have a time derivative. But in non-relativistic physics, time derivative is equivalent to taking 2 times the spatial derivative. Remember the Schrodinger equation. And so from one operator, we can take commutator with P and H and raise the dimension. And from the Schrodinger algebra, one can show that by commuting the operator with the Galilean boost and the spatial conformal transformation, one decrease the dimension by 1 or 2. So when we go down, at some point we reach the bottom of the ladder, and the bottom of the ladders are the primary operators. These primary operators, they have quite simple 2-point function. The 2-point function, a primary operator, can be determined up to a numerical coefficient by the symmetry. So it has this form. 1 over t to the dimension of that operator times the exponent of the dimensionless ratio of x squared over t. Non-relativistic conformal field theories turn out that starting from 3-point function, we start to have non-trivial functional dependence in the correlation function. Let's go to one example of non-relativistic CFT. The most trivial example is the example of free particles. So if we have free particle written in the field theory or second quantized formulation, we have an action that is written here, and one can derive by trivial power counting the dimension of this operator to be d over 2. Again, the time has to be counted as space squared in this power counting. This is probably not this is a trivial example of a non-relativistic CFT. There are several other interacting examples. One example is non-relativistic anyons. In 2 + 1 dimensions, statistics of particles can be not only bosonic or fermionics. We can have anyonic statistics. And I consider particles that are abelian anyons with some statistics. One can define non-relativistic conformal field theory where the only parameter is the dimensionless statistics, because we are lacking any dimensionful parameter when defining the theory. We see that it is scale invariant, and one can check that it's also fully conformal invariant. There is a more realistic theory, realistic in the sense that it has been realized in experiments in nature. It's called spin 1/2 fermions at unitarity, and it is realized in cold atom experiment, but also approximately by neutrons in nuclear physics. To define the notion of fermion at unitarity, one can approach from 2 + 1 dimension. So consider 2 + epsilon spatial dimension. So d here is equal to 2 + epsilon. When we do power counting with this Lagrangian, we find that the dimension of this operator lambda is 0 in 2 + 1 dimension. The interaction is marginal in 2 + 1 dimension. In 2 + epsilon spatial dimension, it becomes slightly irrelevant. But the beta function has a non-trivial interacting fixed point at a value of lambda star equal -2 pi epsilon. That is, the calculation is still conservative when we go slightly above 2 dimensions. So there is this fixed point corresponding to particle interacting with spin 1/2 particle with a slightly attractive interaction. And the question one can ask is, does this fixed point survive at d equal to 3? And the answer is that this survive up to d, well, including at d equal to 3 and up to d slightly less than 4. So in 3 dimensions, the problem is actually known the interpretation of this fixed point is very intuitive in quantum mechanics. So consider a trivial problem, a very simple problem of a bound state in quantum mechanics. Two particles interacting with the potential. For simplicity, I choose that to be a square well potential. That is, the potential energy is minus V naught. For r, the distance between two particles less than some r naught, and 0 outside the potential. So this is a problem that is solved in when we study quantum mechanics, and we know that there is a critical values of V naught at which the bound states start to appear. If the potential is too shallow, there is no bound state. If the potential is more deep than a critical value, I think I have the value here, 1 over r naught squared times some numerical factor, then the bound states start to appear. Now, the unitarity limit, so-called unitarity regime, in quotes, is the regime where we fine-tune the depth of the potential to exactly this value, so that there is one bound state at 0 energy, and then shrink the size of the potential to 0. Always keeping one state, one bound state with 0 energy. So this is the regime called the unitarity regime. It's called so because S-wave scattering amplitude, S-wave scattering cross-section saturates unitarity limit regime. Quantum mechanics, this situation corresponds to a low energy resonance where the, so let's just recall, if we have a resonance, S-wave scattering, then the scattering amplitude is given at low energy or low momentum of incoming particle by this formula, where we have here 1 over this denominator has been expanded in power of k. I think I have a typo here. It should be r naught k squared. So it's an expansion over power of k, where we have in the unitarity limit, the 1 over a term goes to 0 because the scattering length a goes to infinity, and the next term also goes to 0. The r naught is the size of the potential, also goes to 0. So in the unitarity limit, the scattering amplitude between the particle does not depend on anything. It's non-trivial scattering, but it's the scattering amplitude depends only on the energy of the incoming. No dimension full scale parameter appearing in the formula. And so in this regime, we have a conformal theory with non-relativistic conformal symmetry. But the unitarity regime can be understood directly without taking the limit r naught goes to 0. That's something I would like to describe now. So let's come back to quantum mechanics. So in quantum mechanics, we usually talk about the wave functions. And with particle carrying spin 1/2, one can define the state of n particle by specifying the wave function as a function of the coordinates of spin up particle x1 to xm and the coordinates of spin down particle y1 to yn. Fermionic statistics requires that this wave function is antisymmetric when we exchange two x's, and it's antisymmetric with respect to exchanging two y's. Now, suppose we take one particle with spin up and one particle with spin down and let them approach each other. Usually in quantum mechanics, the wave function you have regularly at least when these two particles goes together. But in the theory that called theory of unitarity fermions, it turned out that this wave function has a divergence of the type of 1 over x minus y when the coordinates of these two particles approach each other. Why 1 over x minus y is special? That is because if we look at the Hamiltonian, if we imagine defining the Hamiltonian just as the sum of the kinetic energy of the particle, acting a Laplacian on 1 over r annihilated, except for a delta function at 0. So the definition of the theory of unitarity can be given as a theory where the Hamiltonian is defined this way, and the wave function has a 1 over x minus y divergences when the two coordinates of two particles with opposite spin approach each other. But we have a rule that when we act the Laplacian on the wave function, we throw away all the delta function. Turn out to be a consistent way of defining quantum mechanics, where the Hamiltonian is a Hermitian operator. And I'm simplifying the boundary condition a little bit here. The boundary condition must be that is singular, and then the next term that is constant vanishes, and only the linear term in x minus y is not vanishing. And all this expansion is over odd power of x minus y. Now one can ask the question, as one usually asks in quantum field theories, what is the spectrum of local operators? So here in quantum mechanics, the local operators are, the simplest local operator is the annihilation operator of a single particle, psi of x. That is an operator that acts on the n particle state, give us an n minus 1 particle state. If, for example, if it acts on a one body state, it gives us a vacuum with the amplitude that is the, by definition, the wave function of that particle, of that one body state. So this is the operator that is the charge 1 or charge minus 1, if one is being pedantic, and its dimension 3½ in 3 plus 1 dimension. Okay, so now the first non-trivial operator is the charge 2 operator. Quantum mechanics, if we define, if we have a two-body state, we can compute the matrix elements of psi x, psi y, the annihilation of a spin-up particle at point x, and spin-down particle at psi y. Acting that on the two-body state gives us the vacuum, with the amplitude being equal to the wave function of this two-body state. In order to get the local operator, we want to take x and y and shrink the distance between them to 0. So we want to have some operator that looks like psi up x, psi up x. Now, this operator is problematic in our theory because if we look at its matrix elements, the matrix elements measure the wave function at coinciding point. The coordinates of the two spin-up and spin-down particle coincide. But we have just defined the wave function, well, the Hilbert space of our quantum mechanics, to consist of only the wave functions that are singular, as 1 over x minus y in this limit. So this operator doesn't exist. Instead, we have to define an operator more carefully by keeping the distance finite, take the certain limiting procedure when we take the product of two operator multiplied by x minus y. And only then we have a operator with a finite matrix element. These matrix elements of this operator that I defined as O2 in between a two-body state and the 0 measure the asymptotics of this two-body wave function when the two particles coincide with each other. The coefficient in front of 1 over x minus y, which is finite. And so this operator is an operator that knows about the interaction in the theory. Particularly, the dimension of this operator is not equal to the dimension, twice the dimension of the charge 1 operator. It is a charge 2 operator with a dimension equal to 2, not 3. In a free theory, such an operator with carrying charge 2 would have dimension equal to 3, not 2. Now, we can go a little bit further. For charge 3 operator, it becomes quite a non-trivial problem. It's a problem of finding the asymptotic behavior of the wave function of 3 particles, 2 with spin up, for example, and 1 with spin down. The only thing that is required is that this wave function when one of the pairs of opposite spin particle approach the wave function diverges a 1 over x minus y. A 1 over x1 minus y, 1 over x2 minus y. But it turned out that when all three coordinates shrink to the same point with the same rate, the asymptotic behavior of the wave function is quite non-trivial. That is a three-body problem in quantum mechanics. And in 1970, Efimov miraculously solved this problem. So with the name of Efimov usually is associated the so-called Efimov effect, that is the behavior of the wave function of bosons. But in the case of fermions, the problem defined this problem, solving the problem, tell us the dimension of the three-body operators. It turned out that this wave function behave like r to the power of some transcendental number when all the coordinates shrink to 0 with the same rate. That is keeping the triangle similar during this procedure. And then one can define the charge-free operator by taking an appropriate limit, requiring that this operator has finite matrix element between, say, a three-body state and a vacuum. And we find that the dimension of this operator turned out to be 4.2727. That can be compared with the free theory. The operator, corresponding operator, has dimension 5.5. Let me show you the equation from which this transcendental number is obtained. This is from, I won't be able to explain this, but what Efimov method has allowed us to solve the three-body problem and derive this dimension. So the dimension can be written as 5 half plus s, where s is a solution to certain equations that depends on the angular momentum of the operator. For the operator carrying angular momentum L equal to 0, this is the equation, and it has an infinite number of solutions. The first one corresponds to operator with dimension 4.666. For the L equal to 1 operator, the equation is slightly more complicated, and the first operator, actually the lowest dimension operator is found in the L equal 1 channel, and it has dimension 4.27. Okay, so the charge 4 operator, when we go further, it turns out that there is no analytic way to find the dimensions. Dimension of operator that's larger than 3 can be found only numerically. And one of the way to visualize this dimension is to use the so-called state operator state correspondence, namely that each primary operator O corresponds to an eigenstate of n of O, where n is the charge of this operator, fermions, unitarity fermion in a harmonic trapping potential. So this fact can be shown purely algebraically by constructing this state. One first acts on the vacuum the creation operator, that is the Hermitian conjugate of that operator. We get some state with n particles all sitting at the same point, and then we evolve that state using the Hamiltonian in free space, basically in Euclidean space, in Euclidean time, so that the wave function smear out a little bit into a roughly a Gaussian shape in wave function, and one can show that that wave function is the wave function of the Hamiltonian in harmonic potential. Numerically, the value for 4 particles, for charge 4 operator has been determined to be around 5, compared to free theory where the dimension would be 8. So interaction between the particle is attractive interaction, as a rule, reduce the dimension of the operator. The 2-point function can be found. Maybe I will skip this slide. Let me recall that symmetry required the 2-point function to have a certain form, and in momentum space, it can be thought of as the some fractional power of the propagator of a single particle. That's a requirement of the Schrödinger symmetry. In the real world, the non-relativistic conformal field theory is approximately realized by neutrons by accidents in nature. Two neutrons almost form a bound state. If the interaction is slightly more attractive, it would form a bound state. The scattering length between two neutrons is almost infinite. It's minus 19 Fermi. And minus means that it's slightly not enough attraction to form a bound state. That can be compared with the next correction in the effective range expansion, which has a natural size 2.8 Fermi, the size of the range of the nuclear interaction. So the non-relativistic conformal field theory is valid approximately within a range of energy determined by this two-length scale, which is 2.1, well, 0.1 MeV and about 5 MeV. Almost 2 decades of energy is covered by the non-relativistic conformal field theory. And one can show that, I will try to tell you that this leads to a power law behavior of scattering amplitude, scattering rate of processes where final state neutrons are emitted. And this was done in a paper that Hans Hammer and I wrote in 2019. We pointed out that there is a non-relativistic version of Georgi's unparticle physics in nuclear physics, and we call that a phenomenon of nuclear physics. Okay, consider a scattering process where we have two particles, A1 and A2. This could be some nuclei or some strongly interacting particle colliding, and then becoming one particle B and a bunch of neutrons. Here we have 3 neutrons, but it can be any number of neutrons. Now, suppose we consider we look at the energy of this particle B. Its energy spectrum is continuous, and it has an endpoint. There is a maximum energy. When the energy of B is close to maximum, all the neutrons have to be going in the same direction with the same velocity. And in this kinematic regime, they keep interacting with each other. You recall that the scattering length with the neutron is very large. So roughly speaking, they have to go before the distance between them exceed 20 Fermi to stop interacting. This is why the particle B is already decoupled from the system. So in a certain kinematic regime, one can argue based on this physical picture that the scattering amplitude has to be factorized into product of two processes. The first primary process, A1 and A2, create the B and some composite objects called U. This composite object propagates a long time before it decays into 3 neutrons. So taking the product of these two probability, we get the probability of the reaction. This is valid only when the energy scale of the primary reaction, this part of the Feynman diagram, is much larger than the energy that these final neutrons have in their own center of mass frame. So let's draw some conclusion from that. So here I'm looking at d sigma over the E, where E is the energy of the particle B. So here near the end point, all these neutrons are moving in the same direction, and the scattering amplitude is proportional to the decay rate of this object U going to, say, 3 neutrons. So this object U is this one. But U has to be thought of as an operator in the non-relativistic conformal. It's the only thing that exists here. So it's an operator where the decay rate of U to the final product is equal to the imaginary part of the propagator of U. That imaginary part, we know how to compute. It depends on the dimension of the operator, and using kinematic consideration, we can relate this imaginary part with the distance to the endpoint. Turn out to be E0 minus E to the power of delta minus 5/2. But delta is the dimension of that U. So near the endpoint, we have a universal power law behavior of the cross section dictated by the interaction between the neutrons that respects conformal invariance. So so this alpha depends on the number of neutrons that is emitted. For processes where we have 2 neutrons that is emitted, for example, this alpha turn out to the delta is 2 as we have derived, and alpha is minus 0.5. So that means that the interaction between the neutron actually make the scattering rate going up, like 1 over square root of the distance to the endpoint. And that fact is already known in the 1950s. Let's go up, very close to the endpoint, it went down because very close to the endpoint, the non-relativistic, we are outside the range of the validity of non-relativistic interacting conformal field theory. For 3 neutron emission, this number delta we have shown that it's equal to 4.27, and alpha then is 1.77, and for 4 neutron we can also predict that the behavior should be E naught minus e to the power of something close to 2.5. Now the Watson and Migdal formula that was derived in the 1950s tell us that d sigma over d, well, the distance to the endpoint here is written as ENN, that is the kinetic energy of the 2 neutrons in its common center of mass. It actually have a analytic form in the regime where we take epsilon n, that is this 0.1 MeV, very small energy scale to 0. We reproduce the power 1 minus 0.5 shown in the previous slide. One can try to compare that with experiments. So in the 1980s, people were interested in the interaction between 3 neutrons, and one of the reactions that was looked at is the so-called radiative capture of pi minus by a triton. A triton is a bound state of a proton and 2 neutrons, and one can make a pion going around it, forming an atom, pionic atoms, and waiting a little bit, the pion would falls into the nucleus and absorbed by the proton, and we get 3 neutrons. The processes that is written here is slightly more rare process where we also have photons that is emitted from this reaction. The data from the 1980s, unfortunately, is not accurate enough in the regimes that we are interested in. So we look at the more recent simulations of this process, where these points are the points of the numerical point that one get by simulating the process using sophisticated nuclear physics input. So you have to look at the comparison between this point and this line. This line is basically e to the power of 1.77. Find that the behavior of the cross section near the endpoint almost will follow very well the power law behavior that one predicts. This line down here is a line that compares the result of the same simulation, but when the final interaction between the neutrons is turned off, they can turn off the interaction between the neutrons, and then this point turn out to follow the exponents that one obtained if we assume that the neutrons are free particles, non-interacting free fermions. So we compare both. We can confirm both behaviors of a theory where neutrons interact with resonance interaction, when in the theory where neutrons don't interact at all. So here to give you a sense of how sophisticated that calculation is, they use nucleon potential, so-called argon potential, 40 adjustable parameters. And there is also a 3-body force thing on top of that. But the claim that we made here is that independent of the details of the nuclear interaction, the power law behavior of the cross-section of this process that follows it dictated simply by a very simple conformal exponents in conformal. What we have done, basically, you have made use of the fact that in the theory of strong interaction, there is a window in energy where the neutron interact non-trivially, but following a simple conformal field theory. QCD we have in the UV a theory called QCD, and we run it, and we just follow the neutron. The neutron linger somewhere here for a long time in the renormalization group time, unitarity neutrons, and then only at very low energy, much less than 0.1 MeV, it becomes described by free fermions. So this unitarity fixed point is not exactly lying on our renormalization group flow. This fixed point, however, determine a lot of behavior of the cross-section because we flow near it. This fixed point has one relevant deformation, that is the scattering length, and infinite number of irrelevant deformation. The most non-irrelevant of each of these is the effective range correction. So we have asked the question whether we can compute correction to our prediction that comes from the deformation. So let me just tell you very briefly how we do that. We use conformal perturbation theory. That is, we say that the theory of neutrons can be thought of as a conformal field theory plus perturbations. So there is a relevant operator, turn out to be O2 Decker. O2 has a coefficient that is proportional to the inverse of the scattering length. And there is one more operator that is irrelevant, so parameterizes the scattering rate, the effective range of the S-wave scattering. The contribution for O3 Decker can be computed using conformal perturbation theory, and we can then predict the power correction to the power law that we have derived. So, for example, in the case of technically what we do is we take the path integral, but expanding these perturbations deformation in power series over the coefficients, and the correction becomes the problems of computing 4-point function in nonrelativistic conformal field theory, which in this case one can do. We don't have a very good technique to do that, but we can insert complete set of states 4-point function and compute the corrections. The correction in scattering lengths turn out to be 1 over m times omega, so it becomes important when omega goes to 0, but normally it is suppressed. Effective range correction is a puzzle for us because we spend a lot of time computing various integral before noticing that the coefficient in front is 0. So this vanishes in physical dimension b equal to 3 for some reason that we do not completely understand. And it has also been observed in the correlation function for large charge operators that recently have been considered by Orlando and Revert. An open question that we don't know how to solve is how one can one resum all the correlation, all the correction proportional to 1 over a, and get the 2-point function not at the 2n of the RG flow, but along the whole RG trajectory from the unitarity fixed point to the free fixed point. For 2-point functions of the charge 2 operator, that has been done by Watson and Migdal, but for charge 3 and higher operators, we don't know. Maybe in the large charge limit, it's possible to this calculation. So let me conclude. We have a set of very interesting non-relativistic field theories that have conformal symmetries. One prominent example of such a theory is fermion sedimentarity. This theory is approximately realized by neutrons in nuclear physics, and the conformal symmetry leads to power law behavior of differential cross-section of certain processes near threshold. We started developing the technique of non-relativistic conformal perturbation theory, but it's fair to say that the full power of non-relativistic conformal symmetry is still to be explored. There are some questions that would be interesting to understand. I've presented to you a physical argument why the amplitude of certain process has to be factored out into the product of a primary process and the process of decay of a composite object into the neutrons. It would be nice to understand this more rigorously and see whether there are factorization theorems that one can prove. One can also try to address not the total cross-section integrated over the whole phase space of all the neutrons, but more refined observable that, for example, the correlations between the energy or the angles between the neutrons. These are the things that experimentally people now can measure. There are also proposals of studying processes where 6 neutrons are emitted from the initial state. So something that one, some observables from analogous to one used in collider physics may be useful here as well. Thank you very much.
Yeah.
Hey, just a possibly silly question. Is there a relation to relativistic conformal field theories? So if I give you like a set of scaling dimensions, is there a relation you can
So one way to relate is to take, so one can take the relativistic conformal algebra and select out all generators that commute one light cone momentum. So then the smaller set of generators form a Schrodinger algebra of space with one less dimension, visual dimension. So there is a certain connection with this light cone reduction.
I see. Okay, thanks.
Thanks for a nice talk. So, around the free fix point, there was this EFT by Mark Weiss, Martin Savage, Kaplan, and friends, right? For these nuclear interactions. So, can you, for instance, this 2-point function of O2, can you see that it agrees on the usual line?
Kaplan and Weiss and Savage, they are actually describing this fixed point. They do not formulate their power counting scheme as expanding around a fixed point, a renormalization group fixed point, but de facto they were doing that. I think
You were just doing free particles with like contact interactions,
yeah,
right?
free particle with contact interaction, but they sum up certain diagrams. They say this diagram, the power counting is different from the naive power counting.
Right.
The fact that the power counting is different from the naive power counting means that the certain operators now have a different dimension. So de facto, actually, they are doing power counting around this fixed point. The first person who realized this, there is a RG interpretation to the power count, to the power counting. I think maybe such depth and equals context of condensed matter.
Actually, for the resummed result, can you say a little bit how they did it?
The result for 2 particles is extremely simple to obtain. That's because in non-relativistic physics, the only diagram when we have 2 body scattering is S-wave interaction diagram. There is no particle hole creation. When we have 3 particles, the number of diagrams becomes more.
So also on a paper by I believe Kaplan and his collaborator, they looked at baryon scattering the baryon S matrix to they said that when you have enhanced symmetry, you can see if something could be at the phase shift. And entanglement symmetry.
I haven't thought about that.
Okay, if not, then let's take thumbs on again.